Hello, my name is Ali Pakniat, and in this short video, I'm going to introduce you to the field of control, or to be more precise, the control of dynamic systems. So informally speaking, when we say dynamic systems, then something is changing over time. And that's something we refer to as the state of the system. What makes a dynamic system indeed a control system is the presence of input to be decided. And depending on different notions of time, state, and input, different mathematical tools have been developed, which overall they constitute the theory of control systems. So let's begin with time. Our notion of time might refer to a continuous variable, which means that t takes any values in real numbers, or usually a subset of real numbers that begins from an initial time. Or our notion of time might refer to a discrete variable that takes values from a countable set, t0, t1, t2, tk, and so on. Or for simplicity of discussion, we can consider only the indices, which are 0, 1, 2, and so on. There is a slight distinction here where in this notion, I'm detaching the dependence on the actual value of time, the physical time, but for the sake of this discussion, we do not make this distinction. So our notion of state might also refer to a continuous variable taking value of a set which, for the sake of this discussion, we consider finite dimensional Euclidean spaces, but there is not much effort to make a generalization over different types of manifolds, but let's forget about this distinction at this moment. And our notion of state might refer to a discrete variable that takes from a countable set or a finite set. We get to that slight distinction shortly. Again, our notion of input might be a continuous variable or a discrete variable, which means that the value of the input at every time t might come from a set U, which is a subset of an Euclidean space, possibly of different dimension. And our notion of discrete input is something that takes values from either a finite or countably infinite set. So most importantly, our distinction of time makes the mathematical tools different. If you have continuous time, then the system is described, the dynamics of the system is governed by a differential equation, which means that x dot, which is also dx over dt, is a function of the current value of the state, current value of the input, and the current value of time. Or if we have discrete time, then we have an update form of dynamics that gives the next value of the state as a function of the current value of state, current value of input, and the current value of time. So remember that I said that in the case of discrete state and discrete inputs, this might come from a finite set. In this case, it is more convenient not to look for a function in this form, but present the dynamics directly by a finite state machine or a finite automata. But for the sake of this discussion, let's assume that this function is available. So the objective in control is to design or select a policy, pi, that determines for us the control action or input u at every time based on the information available at that time. Okay? And different structures can be considered for this design. We can consider open loop control design methodology that gives the value of the input as a function of the initial condition of the system, the initial state, and the current value of time. Or we can consider closed loop control, that the information structure, so the policy, depends on all values of the state that are taken from the initial time to the current time. Or we can consider feedback control policies that has a structure of being a function of only the current value of the state and the current value of time. So there is a huge misconception here that many people think that closed loop and feedback control policies are equivalent, which, as you see in these definitions, they are not. And indeed, when we go to the discussion of stochastic systems or differential games, then we see that in most of the cases, open loop and closed loop policies are more closely related compared to feedback control laws. I hope by this video I could make this distinction. Thank you.